We physicists have held up a long time beginning around 1916 for this. Prestigious physicist one of the pioneers of theoretical physics, Michio Kaku, devoted his life to deciphering the universe's darkest secrets. He has now started a quest to question and possibly change the fundamental rules that govern our existence. Doctor was widely regarded as one of the best scientists of our time. Kaku strikingly recommends that our existence may be settled inside the limits of a dark opening. Simply envision the significant ramifications. Our whole impression of existence epitomized inside the tremendous gravitational draw of these grandiose puzzlers. Be that as it may, what precisely is a dark opening, and how could it become? Go along with us as we dig into this enamoring venture investigating the unprecedented conceivable outcomes disguised inside these enormous peculiarities. Close by, we'll inspect late pictures caught by the James Webb Telescope, possibly reshaping how we might interpret the universe's starting point. Leading researchers claim that black holes are intricate cosmic wonders rather than merely empty voids in space. The gravitational pull exerted by these immense concentrations of matter, which are condensed into unimaginably small areas, is so strong that nothing but light can escape. Despite their invisibility, their significant influence on the material around them makes it clear that they are there. A few dark openings are surrounded by whirling plates of gas and residue, discharging huge measures of radiation and procuring the title of quasars, the universe's stunning elements. Be that as it may, how do these entrancing peculiarities shape? Various types have been proposed by scientists, including supermassive black holes that can be found at the centers of galaxies like our own Milky Way and stellar black holes that arise from the collapse of massive stars. While the exact development instruments stay a riddle, hypotheses range from heavenly breakdown to converges of more modest dark openings or the retention of neighboring stars throughout massive timescales. Late perceptions by the James Webb Space Telescope Challenge laid out hypotheses, especially concerning the universe's introduction to the world. Dr. Kaku, known for his real-to-life sees, features the telescope's noteworthy revelations, including the recognition of universes simply a portion of a billion years after the enormous detonation, systems multiple times bigger than our smooth way. Considering our current understanding, massive galaxies of this size should not have existed at such a young age in the universe. This finding presents a significant puzzle. In light of these perplexing findings, Kaku emphasizes the necessity of rethinking and possibly revising our understanding of the universe's origins. These galaxies, which have billions of stars in them, formed when the universe was still in its infancy. This raises important questions about the evolution of the universe and the fundamental rules that govern our existence. The course of events of cosmic system development portrayed by the new disclosures challenges current models, recommending a quicker and prior development than recently suspected. This interesting riddle might require new bits of knowledge from material science or the advancement of novel strategies for system creation. As appropriately named by the James Webb Space Telescope's ability to provide a novel perspective on the early history of the cosmos, which challenges existing notions and encourages exploration into uncharted territories of knowledge, is demonstrated by the groundbreaking revelation of these universe breakers, Kaku. By analyzing JWST images taken in July 2022, astronomers from Swinburne University of Technology in Melbourne, Australia, led by Evo Lob, achieved a significant breakthrough. These pictures, catching a little part of the sky, uncovered 6 universes of extraordinary brilliance and rosy shade beforehand imperceptible by different telescopes. Utilizing photometric redshift assesses, the group decided the universe's good ways from Earth, uncovering inconceivably high redshift values going from 9.5 to 11.5. This contradicts previous findings and suggests that the light from these galaxies originated more than 700 million years ago. Further examination uncovered the amazingly enormous heavenly masses of these systems, going from 10 to 100 billion times the mass of our Sun, matching or surpassing that of our smooth way. These discoveries went against regular hypotheses of steady system development, proposing a quick change of gas into stars. Furthermore, disparities arose concerning cosmological hypotheses in view of investigations of the enormous microwave foundation, as these systems contain more mass than expected for their particular areas of room around them. The presence of old and red stars in these cosmic systems brought up issues about star arrangement and compound advancement in youthful conditions. To address these differences, researchers thought about elective clarifications, including the likelihood that these articles probably won't be systems yet rather quasars or other dynamic cosmic cores filled by supermassive dark openings at their focuses. These discoveries highlight the intricacy of the early universe and the requirement for proceeded with investigation and refinement of our comprehension. Notwithstanding, the shortfall of unmistakable ghastly marks anticipated from dynamic cosmic cores in these items brings up issues. The arrangement and growth of issue onto supermassive dark openings normally call for investment, making it uncommon at such high redshifts. Another chance is that the models and hypotheses used to decipher the perceptions were imperfect, prompting vulnerabilities about these worlds' development. To uncover the secrets of these extraordinary galaxies and their formation and evolution mechanisms, additional research and investigation are required. These cycles might include the production of gigantic cosmic systems inside a short period of time without depending on consolidations or growth. On the other hand, these worlds may be anomalies that arose under uncommon circumstances or in intriguing districts of room, as opposed to being illustrative of everybody around them. These oddities might actually challenge how we might interpret cosmology or physical science, recommending novel occasions or collaborations past the extent of current models. The annihilation of dark matter or primordial density fluctuations, according to Kaku, may have affected the volume and distribution of matter in the early universe, causing mass variations and faster expansion in some areas. Moreover, proof for new aspects or extra powers, like those proposed in string hypothesis or altered gravity, could affect how we might interpret the universe's essential regulations. While these are hypothetical prospects, they highlight the requirement for additional examination and testing with additional information and further developed models in the years to come. The James Webb Space Telescope, outfitted with a scope of instruments equipped for directing complete examinations, is supposed to give more data about these particular systems and their suggestions for cosmology and physical science later on. In the meantime, a fascinating development is that the James Webb Space Telescope has observed globular clusters, which are ancient clusters that contain millions of stars in a small space. Webb's discoveries uncover the serious brightness of stars inside these groups, alongside an overflow of nitrogen, recommending the presence of Goliath stars. These bits of knowledge offer signs to the development and advancement of these puzzling bunches, giving new roads to investigation in the investigation of heavenly elements and development. In the midst of these disclosures, Dr. Kaku suggests that the JWST may have encountered black holes rather than young galaxies as an alternative explanation for the recent findings. By suggesting that these objects could be monstrous black holes that emerged from the aftermath of creation itself, this hypothesis challenges conventional theories of the formation of galaxies. This idea suggests that these enigmatic cosmic entities are the source of new physics laws that push the boundaries of what we know about the universe. A related theory suggests that the universe itself may be a massive black hole formed when a massive black hole collapses, resulting in the birth of an even larger universe within the black hole's event horizon. Where gravity is extraordinary to such an extent that nothing can escape, space-time becomes twisted, prompting a peculiarity, a place of limitless thickness and curve. A new event horizon within the black hole might open up to a new world beyond our current comprehension, according to some scientists. The charming thought that our universe dwells inside a dark opening settled inside another universe proposes the presence of different universes inside other dark openings. This concept is supported by theoretical models, but there is currently no experimental or observational evidence to support it. This hypothesis, on the other hand, provides a compelling perspective on our cosmic origins, particularly with regard to the events that took place prior to the Big Bang. The Big Bang theory says that the universe started from a dense state of matter and energy about 13.8 billion years ago, but it doesn't say what started it or what happened before it. A few physicists, such as Dr. Kaku, have stayed disappointed with this clarification and endeavor to uncover a more significant clarification for the production of our universe. One convincing hypothesis places that our universe developed from a dark opening in another universe, offering an entrancing viewpoint on our grandiose starting points. This idea was presented by Russian physicist Igor Novikov in 1973 and developed by physicists like Lee Smolin, Nikolai Kardashev, and Stephen Selling. As indicated by this hypothesis, our universe could be only one among incalculable others inside a huge spread called the multiverse, each with its own particular arrangement of actual regulations. Envision these universes as discrete elements, each with its own guidelines and attributes. Some of them could try and house uncommon peculiarities like dark openings equipped for bringing forth totally new universes. How can this be the case? Consider a dark opening a design existing inside the texture of existence, as portrayed by Einstein's overall hypothesis of relativity. Gravity is so strong in a black hole that it twists the fabric of reality and creates a singularity, which appears to have no bottom. However, some physicists contend that these singularities are mathematical artifacts, not physical entities. They suggest that when we push the limits of general relativity, quantum impacts become possibly the most important factor, keeping singularities from arising inside dark openings and leading to new districts of spacetime with one-of-a-kind qualities. These new spacetime areas could be new universes with altogether unique actual regulations, isolated from their parent universes by occasion skylines. These limits go about as undetectable hindrances past which nothing can escape or convey. Within the enigmatic depths of a black hole, this remarkable scenario imagines a cosmic separation between universes, each with its own distinct characteristics. The arrangement of new universes could be happening, growing the limit of our comprehension and uncovering the boundless potential outcomes inside the immense embroidered artwork of the multiverse. There is also the possibility that these newly discovered regions of spacetime are wormholes, spacetime shortcuts or tunnels, offering yet another fascinating path.